Well, I said God, I want 100, and he said, not horrible, but you can do better.
He had just said he had a 60-something.
Yeah.
That's funny.
It was not responding to you. Okay.
Out of context moments.
Exactly. Lesson 9.7. Let's talk about lesson 9.7. Okay. Lesson 9.7, although it's not the last page in your notes packet, it's going to be the last section we do in this chapter. Because I think I copied 9.8 at the time, but timing-wise, I decided to skip 9.8 because we don't do 9.8. We get the chapter test in this week, and we don't have to try and come back to the test right after fall break, which would be a bad
That'd be
idea.
nasty.
Exactly. So, okay, so let's get these notes. Lesson 9.7 is looking at the compare and contrast kind of linear, quadratic, and exponential models. So just knowing which is which, how they relate, and all of that. Okay. So when we talk about a linear model, obviously linear means a line. And the part you're most familiar with for a linear is y equals mx plus b. That's the line you guys know, right? Where m is our slope and b is our y-intercept. Okay? I'm going to say, if we graphed those this semester, we haven't really done any graphing, I don't think, yet. So, okay, so that's linear. Quadratic, which I don't know if you did quadratic first semester, if we do quadratic this semester. But quadratic equations are of the form y equals ax squared plus bx plus c. What am I talking about? We've already talked about these. That was this chapter. Okay, so if it's quadratic, remember quadratic means there's going to be an exponent of 2. Okay, that's if it's quadratic. Exponential we looked at a little bit in chapter 7, so right at the beginning of the year, and that is y equals a times b to the x, and if it's exponential, that means that there is an x in the exponent. Okay, the exponential graph looks like this curve here, runs along the x-axis, and then goes up to infinity. Quadratic, that is a parabola. It's the U shape, yes? Okay. So, first set of examples. Choose a model by graphing. So, graph each set of points and which model is most appropriate. So, if we graph these, 0, 0, 1, 1 means I'm going over 1, up 1. Remember, first number's left to right, second number's up or down. What about negative 1, negative 0.5?
Over to up halfway.
Not up halfway, but down halfway. Yep, left 1, down halfway. 2, 3? Over 2, up 3. This one match with the exponential form? It's got one side that's going up, and it's curving, right? It's not a straight line, so it's going up. The other side would be going sideways. So I agree, this one is an exponential. Okay, ready for B? Negative 2, 11. Somewhere up in here, yes?
Yeah.
It's fine. Okay, so I was left 2, up 11. Negative 1, 5. Left 1 and up 5.
My brain is like not all there to that.
0, 3. Over none, up 3. 1, negative 5. Wait a minute. I say there's got to be a typo here, because this is not making any of them. So I just looked at my notes. This last one is supposed to be 1 comma positive 5. In my notes here, I have the 5 whited out, or the negative in front of that 5 whited out.
So, quadratic.
So, right one up 5. It is a parabola, which means it is which model?
Quadratic.
Quadratic. And that's where I was thinking, dang it, where did I make my graphing mistake? Okay, bottom one. Negative 4, 1. Left 4, up 1. Okay. Negative 3, 3.
Left 3, up 3.
Left 3, up 3, good. Negative 2, 5. Left 2, up 5. Negative 1, 7.
Left 1, up 7.
Left 1, up 7. What is it?
Linear.
That is linear. Okay. So far, so good. Yes?
Yes.
Okay. Look at the next page real quick. I'm trying to pull up the homework real quick. I want to check something.
All right.
I'm so ready for it.
Me too. I'm going to Florida.
I'm staying home.
I've never seen the ocean before.
What are you doing in Florida?
I don't know. I didn't even know we were going until yesterday.
So you don't know if it's a beach vacation, a Disney vacation?
Well, it's the beach.
Okay.
It's not like Disney.
Okay.
Oh, look at Michael.
School lunch participation is associated with the lower body mass index.
That is me.
Okay. Let's look at this next page. As we look at this next page, notice we're not talking about a graph. We just are given this XY, this chart of values, and we are trying to figure out, just by looking at the chart of values without graphing, whether it is linear, quadratic, or exponential. Okay? So, notice there's some information up top. When the x values have a common difference. So when I'm talking about common difference on the x's, that means, like in each of these, you'll notice the x is just, they're all different by 1, aren't they?
Yeah.
Okay? That's what we mean by common difference, when they're equally spread apart. Okay? Then, it is a linear function if the y values also have a common difference. So that means if you are adding or subtracting the same amount each time in the y values, then it is going to be a linear function. Exponential function, if the y values have a common ratio. Well, think about it. If common difference was add and subtract, what's common ratio? Multiply or divide. So if your y values all have a common ratio, so they multiply or divide by the same thing to get to the next one every time, then it's exponential. And then the third example we have is quadratic. Now this is the one that's a little more challenging. The y values have common second differences, which means when you add or subtract the first time, those differences are still different, but then when you add or subtract those, the differences are the same the second time through the process. Okay? Again, examples will make it make much more sense, right? And this is something where we could talk about writing equations for each of these scenarios, but I'm opting not to talk about writing equations. We're just going for the basics here. So, which type of function best models the data? And it says uses differences or ratios as opposed to just graphing it. So, first of all, do my x values have a common difference? my
Well,
x's.
oh, yeah.
Yeah, it's
I was thinking Y.
just increasing by 1 each time, yes?
Yeah.
So now, on y values, we have to figure out, okay, what is it doing each time? How do we get from 0.5 to 1, that we can also get from 1 to 2, from 2 to 4, and from 4 to 8? Are we adding the same number each time?
No, because the first one, 0.5 to 1 is adding 0.5, 1 to 2 is adding 1, 2 to 4.
So right there, we don't even have to go any farther, right?
Yeah.
Once McKiley had the first two being different, we know it's not adding the same number.
It's not linear.
What about multiplying?
Yes.
And if you don't like that decimal, can you just avoid the decimal for a moment?
Yeah.
I would. How do you get from 4 to 8?
You add 4.
Multiply.
But add 4, we don't add 4 the other ones.
Multiply by 2.
So we times 2. How do we get from 2 to 4?
Times 2.
Times 2. How do we get from 1 to 2?
Times 2.
Times 2. How do we get from 0.5 to 1?
Times 2.
Times 2. So we just multiplied by the same number every time, right? Which that means there is what is called a common, do you remember what the word was?
Ratio.
Common ratio. If it's a common ratio, this is what?
Exponential function.
Okay, exponential function, right? Okay. Next one, the x's. I just like to check. Are my x's have a common difference? Or are they just increasing by 1 each time? They are.
Oh, yeah.
Okay, so just double check it. Now, how do I get from -6 to -2? That also takes me from -2 to 2, from 2 to 6, and 6 to 10. Okay, and you can always start at the bottom if you need to, right? How do we get from 6 to 10? Add 4. How do we get from 2 to 6? Add 4. How do we get from -2 to 2? Add 4. And how do we get from -6 to -2? Add 4. So this is called a common what? Difference. And if there's a common difference, it's linear. Okay, well, how do we get from 0 to 0.25 in the same way we get from 0.25 to 1 as we get from 1 to 2.25 and 2.25 to 4?
Well, 4 to 2.5. I don't know. It's gonna be the quadratic function, but I don't believe it.
It's going to be the quadratic because that's the one Mrs. Sargent hasn't used yet, right?
Yes.
Okay,
And also because it's weird.
and because it's weird. Okay, so, that's kind of a good thing to acknowledge that it's weird, okay? Because can we easily figure out we're not adding the same thing every time, are we? Because 0 to 0.25, I would add 0.25.
Yeah.
Well, then 1 to 2.25, I'd have to add 2.25. So I know I'm not adding. So right there, I know it's not linear because there's not a common difference. Am I multiplying by the same thing each time?
No.
And no, because in order to multiply from 1 to 2.25, I'd have to multiply by 2.25. Here, 0 times something, I can't even consider that, okay? So we can't really talk about the whole multiplication thing. So at that point, we want to check into this quadratic, which notice it says it has y values have common second differences. So let's figure out what the first differences are. How do you get from 0 to 0.25? You add what?
Add 0.25 or multiply by. Wait, no. Add.
We want to say add 0.25 because we want to talk differences, so we're talking adding, subtracting. And if you don't know one of these, you subtract the two numbers on your calculator, right? How do we get from 0.25 to 1?
Add 0.7.
You add 0.75. How do we get from 1 to 2.25?
Add 1.25.
You add 1.25. How do we get from 2.25 to 4?
Add 2.7. Wait, 1.7.
Yeah, I like that better. Add 1.75. Now, these are the first differences. What do we need to now check? Second differences. So now, how do we get from 0.25 to 0.75?
Well, you multiply every. No. You
Not multiply, think add, because we're talking differences.
Add 0.50.
You add 0.5 or 0.50. How do you get from 0.75 to 1.25? Add 50. In other words, how do I get from 75 cents to $1.25? You add 50 cents, right? You add 2 quarters. How do I get from $1.25 to $1.75? You add 50 cents again, right?
Makes sense now.
So what is this an example of? Where my second differences are the same. Okay? And so since my second differences are the same, this is quadratic. Okay? As I said, we could talk about writing equations. I didn't talk about writing equations. I opted to skip that aspect. And so we're done.
Yeah.
Your homework is lesson. That would help it happen. Lesson 9.7 in Math Excel.